So here we have the section on use of high-resolution site characterization tools and strategies at tank sites. And I've asked Tom Cady with EPA's Environmental Response Team, they are an arm of the Office of Superfund Remediation and Technology Innovation, to present a case study for a site right near their office in Edison, New Jersey. So Tom will be presenting a petroleum case study, and I'm going to provide some historical perspective and also point to some easily accessible case studies that we've done over the years for things like Triad, where we've applied high-resolution site characterization tools and strategies at the sites like bulk terminals, refineries, gas stations, etc., typically focused on light non-aqueous phase liquids, or LNAPL, at those sites. So, of course, our experience with these sort of tools go back to the early Triad days. In fact, one of the earliest Triad case studies was at a series of gas stations and petroleum sites in South Dakota in 2004 and 2005. I've shown in the upper right, just you can still Google and find that document online. But essentially in 2004, 2005, the South Dakota Petroleum Relief Compensation Fund and the State Department of Environmental and Natural Resources and a series of property owners and their consultants got together with the goal of rapid characterization, accurate development of accurate conceptual site models, and to establish clear cleanup goals and move project forward at what were a series of legacy sites. 10 years or older, that many of them had assessment type activities done. Some were closed, but none of them had been formally addressed and closed for all of the petroleum constituents. So again, there were a number of folks involved. I mentioned South Dakota Petroleum Relief Compensation Fund, the state regulators at the Department of Environmental and Natural Resources, all the property owners. They also had a series of technology vendors who participated. In this case, I believe it was Columbia Technologies using their smart data solutions and one of the earlier versions of the membrane interface probe, which was available and in use in the early 2000s. So what did it look like? Well, here we see our typical output from the MIP on the left there. As you move down, you see conductivity, and as you move left to right, you are essentially going down in depth. And you can look at conductivity, speed of the push. You get a response from the flame ionization detector, or FID. You get a response from the photoionization detector, PID. And also, in this case, they have an ECD, which is specific to chlorinated organics, and you don't get a response with that one. So even in this case, you know that you're looking at petroleum hydrocarbons, and indeed, when they go back in at those depths, in this case between about 5 and 7 feet, 5 to 7.5 feet, those are your highest PID and FID responses, and also where you find your highest concentrations in soil and groundwater. And you're looking at BTEX compounds, benzene, ethylbenzene, toluene, xylene, and others. MTBE is included as well. But on the right, those are the types of outputs that you typically get from in this case, this was Columbia and their smart data solutions, but you see a series of direct push, some interpretation of lithology on top and bottom there in gray, and then in the middle, most of the MIP response at that particular site. So how is this project different from the way many projects have been done in the petroleum universe? Well, it certainly elevated communication and cooperation, in this case between the Petroleum Relief Compensation Fund and the state regulators. And in some cases, those relationships between those programs and those state regulators are very collaborative, and in other cases they can be somewhat adversarial. But the relief compensation funds typically manage the funds that are doled out through a tax to provide for cleanup, and then the state regulators run the delegated tanks program. And In this case, they did a one-day systematic planning effort, so that's for all 5 sites. That resulted in a 2-week field effort, mostly driven by MIP, but also there were soil, groundwater, and product samples collected. And at the end of it, they were actually able to develop a correction action plan for all 5 sites. So that was a key goal of moving sites forward, getting them unstuck, if you will. They also found 3 previously unknown underground storage tanks that they were able to locate and remove, and that is often the case at some of these sites with the unknown unknowns where we didn't expect a tank to be. Sometimes these high-resolution site characterization tools allow us to locate some of those that can be problematic later. And of course, in this case, we're looking at a huge quantity of data points, 350,000 points generated from the MIP data, with 25 soils, 13 groundwaters, a product collected and analyzed from one of the sites. And at the end of the day, that resulted in a no further action determination and closure of one site. 2 of the sites required additional remediation and some vapor mitigation, and then additional compliance monitoring. And 2 of those sites were moved into a monitored natural attenuation remedy. So, and ultimately, what you see here is just the 5 different sites, but some estimate of what a conventional investigation may have looked like if we assume 1 data point on the top there for every 2.5 feet. That's a screening with a field ionization detector in the field, and then the collection of 1 soil sample within that boring. We can get something on the order of about 1,403 pieces of information, total data points. But using the MIP tool in this case, where you're getting 20 data points per instrument per foot, you're getting measurements of conductivity, you're getting responses from the PID, the FID, the ECD, even temperature of the probe to ensure that you're getting good volatilization for the membrane interface probe to work properly. And you end up with something on the order of about 350,000 data points for a very similar cost. In fact, and you go to the bottom of this and you look at some of the money that had been spent on the previous assessments, you're looking at, you know, anywhere from 30 to 100,000 US dollars in 2005 to what the triad assessment costs, which were on the order of about $25,000 to $30,000 at each site. So if you look at one of the sites in the middle, for example, the Severson service site, you'll see they had already spent more than $100,000 on assessments, and they were able to come in for about $30,000 and at least develop a corrective action plan and move those sites forward. So high density, high resolution information provided early on at a triad site, and this one is easy to Google and find that case study. It's still available. So what were some of the challenges for us in the early high-resolution site characterization applications in the underground storage tank program universe? We had a number of challenges in the early days, and they are surprisingly not too dissimilar from the same types of findings that we had in Superfund optimization. But the challenges we had in the tanks universe, of course, are funding. The type of funding that's often available for assessment and cleanup are not the types of dollars that might be available for a Superfund site, for example. And again, the funding mechanisms vary with all of the various petroleum funds and the complexities of those relationships with the state regulators in each state, so that's going to vary as well. Of course, in the early days, many of our conceptual site models, particularly for light non-aqueous phase liquids or LNAPLs, really had what we call kind of a pancake model, where we assumed that the product would go down to the water table and then sort of accumulate as a little pool of liquid on top of the water table. And it turns out that LNAPL sites are just as complex, or as DNAPL sites, and we'll show you some of that. And then, of course, these programs, like I said, these tanks programs, they're delegated to states and tribes, and so that provides a lot of flexibility for them to use various tools, but it also results in a lot of variability when you try to look at something from a national perspective, or roll up costs or things like that. And also there's differences in things like the regulations, the mechanisms they use to fund the projects, and frankly, in different parts of the United States, the availability of qualified contractors who could deploy high-resolution site characterization tools. But At least at the same time, we were having a similar experience in the Superfund program and learning from the Superfund optimization efforts. And it turns out that it's pretty similar in the tanks world, in the petroleum universe as well, in that the cost of remediation, we usually spend significantly more on remediating sites than we do for characterization. Certainly in the early Superfund days, we had a lot of experience with it needed improvements to how we developed and used our conceptual site models, and some of those early poorly designed conceptual site models led to poor remedy performance, which ultimately increases costs and leads to remedy inefficiencies. But of course, this provides an opportunity for us to come back as our high resolution site characterization tools and strategies improve to come back and look at some of these sites and think about how we might apply those lessons learned. So certainly our understanding of the complexity of light non-aqueous phase liquids, or LNAPLs, has evolved over time, and we see that highlighted in some of our guidance and experiences shown here. For example, in the middle, just a couple of pictures that we actually found from some early EPA documents depicting our conceptual site model of how LNAPLs behaved in the subsurface, and you see it sort of pooling up as it hits the water table, or pooling up on the water table and then entering into a well. It turns out that those types of behaviors are actually rarely the case, which means that there's some bad news. Our LNAPL bodies can be quite complex, like our DNAPL sites. We have situations where LNAPL may not even enter a well, even though it's screened within the body or right next to that body. That's one of the reasons why people are looking at transmissivity as a way to measure some of these things. That's gaining some traction. But there's also good news, right? Mobile NAPL is pretty stable under prevailing hydraulic conditions, and that's important, prevailing hydraulic conditions. If you have sites with highly variable hydraulic conditions and LNAPLs, in our experience, that can lead to some interesting placement of LNAPLs in places where we wouldn't, our conventional conceptual site models would not assume it would be. But we can reliably map the structure of those LNAPLs with our tools, like some of the laser-induced or optical induced detectors, as well as the membrane interface probe. We can map out these things with near surgical precision, which really helps us hone our remediation strategy in on sort of the LNAPL as the source of dissolved phase contaminant, which oftentimes is leaving a site or driving risk, and really going after those source areas and potentially closing. The states have some options to potentially close sites under a variety of programs, like risk-based corrective actions, petroleum mixing zones, and low-risk closures, where some amount of product can still be, or LNAPL material can still be left in place, and the site can be closed using risks and other techniques. And of course, on the right, on the upper right, I'm showing an example of an article that came out in Lustline. It is for the leaking underground storage tank community. These are all the state regulators who deal with gas stations and underground storage tanks housing various petroleum products. And this gentleman is a regulator in Minnesota, Paul Stock, and he has a great little article in there talking about using laser-induced fluorescence to find LNAPLs. And I've put some quotes there from the article, but some really interesting findings in that, they immediately found that LNAPL does not always float on the water table. They had sites where the majority of the mass was actually found below the water table, which can have profound implications for remediation, particularly at sites where they were considering soil vapor extraction and they had submerged LNAPL. Obviously, the soil vapor extraction would not be very effective against a submerged LNAPL, and they had many of the same assumptions that we did in the early days of how LNAPL behaved in the subsurface, and they assumed that it would simply follow the water table gradient, and the LIF data rather showed them that that was rarely the case. They even had incidences where the LNAPL was migrating in a direction opposite of the hydraulic gradient. Turns out that, like other contaminants, LNAPLs will follow that path of least resistance, and the distribution in the subsurface is really driven by the geology and the hydrogeology components of it. And then finally, We have a site, a great little case study we put out in 2010. It's from a site in Illinois, and it's looking at streamlining vapor intrusion and product removal at sites using the triad. And this is one that you guys can check out, and one of the early days of us using I think it was the Rapid Optical Screening Tool, one of the LIF tools to map out product, and in this case differentiate product. We had a number of refineries, different fuel types, gasoline, diesel, etc., all under the subsurface of Hartford, Illinois, with Superfund really gets involved in these types of sites, but in this case there were actually homes catching on fire from vapor intrusion of some of those LNAPL components reaching explosive levels, actually reaching the lower explosive limit, and several homes caught on fire. So it's a very serious site, and they tried to go in with some of the laser-induced fluorescence tools, map out where all of that material was, and we had very similar findings, finding submerged product. This site happens to be near the Ohio River, which highly influences the groundwater levels there, and you can get significant fluctuation in groundwater levels. So like they found in Minnesota, we had at this site, there was many places where the LIF indicated they actually had NAPL submerged as the water table rose in accordance with the nearby river. So that's a great case study to check out. And also the correlation of using the CPT rigs to try to understand the distribution of clays in the shallow subsurface and how those impacted where vapor intrusion was happening at the site. So very interesting. So in 2015, the Office of Underground Storage Tanks, EPA's Office of Underground Storage Tanks, developed a technical guide for addressing PVI, petroleum vapor intrusion at leaking underground storage tank sites. And this was something that was really needed in that people were able to address other mechanisms or means of exposure, typically in the aqueous or soil, in the aqueous phase or in soils, but the programs didn't necessarily have a great way to address vapor intrusion. So this guidance really helped. And a couple things I want to point out on it is their reliance on and sort of looking for development of a conceptual site model. In this case, so one of the things they're asking you to do in one of the first steps after you've determined if there are any immediate threats is to do site characterization and develop a conceptual site model. To understand and develop information about the full extent and location of the contamination. That's the location of the contamination in space. And also they mention other things to consider in your characterization efforts below. In this case, preferential pathways, be they natural or man-made. And in fact, we find this is the case where these are preferential pathways or ways for contaminants to easily move at sites in natural environments through gravel lenses and channels, sand channels. Certainly karst terrain presents significant challenges. Bedding panes, fracture joints, and faults in consolidated rock can all be sort of preferential pathways. And many times we also find those man-made components as well, utility corridors, sewer lines, sumps and drainage pits, and those types of things also typically end up being important for contaminant migration at sites. One thing that's interesting, if we dive a little bit deeper and we look at sort of the recommended steps, again up in the upper left, assessing and mitigating the threats to the safety of folks, that's the first step. Once you get through that, you actually develop a conceptual site model and do your characterization. And then you have to do something called delineating a lateral inclusion zone and determining a vertical separation distance. In other words, determining when you have either dissolved phase product or LNAPLs near a structure, when do you need to do vapor intrusion type investigations? And they've gone ahead and actually specified those distances. If you look in the upper right hand corner, specifically if the distance for contamination is greater than 6 feet for dissolved contamination beneath a building, or 15 feet for LNAPL, then you don't need to do a VI or vapor intrusion type investigation. If the distance of contamination is less than those indicated depths, they do recommend going in and doing some vapor intrusion investigation. So 15 feet for NAPLs and 6 feet for dissolve phase. So here we have just some examples in the middle. We have a leaking underground storage tank. We have a dissolve phase. This is how you determine your lateral separation distance. How far away from buildings do you have to need to be before you're not in the plume and you don't have to worry about doing VI. If you are closer to a home than this lateral separation distance, that's where you need to look at the 6-foot and the 15-foot intervals as sort of basic guidelines of when vapor intrusion investigation is needed. And the research shows that petroleum hydrocarbons tend to attenuate over shorter distances than chlorinated aromatic hydrocarbons do. So that's good news for many of these tank sites. But again, vapor intrusion still needs to be addressed. And my question, having looked at the guidance, would be, I'm not sure how we could have done this in the absence of high-resolution site characterization techniques, tools, and strategies. In other words, it's really difficult to go to a site and determine that all the nearby buildings don't have dissolve phase or product within 6 or 15 feet of them, and then driving a vapor intrusion investigation from that. That can be time-consuming, expensive, and costly if you're not at least employing some of those high-resolution site characterization tools and strategies. So even at tank sites, the importance of the conceptual site model has continued, and here I'm just highlighting some early Superfund guidance in red that we use to help develop that conceptual site model lifecycle process, or to help us bolster that effort. And so even if you go back to some of the EPA guidance, which was buried in typewritten documents, you could find things like in 1988 where they said conceptual site model was used to assess the nature and extent of contamination, used to guide remediation system operation, refined throughout the life cycle of the project. All of these features should be included in a CSM. These are all the types of things that we were trying to get Superfund and others to integrate into their conceptual site models, and indeed that took place over time. And one of the great case studies, this one is from 2006. I worked on the site prior to coming to the agency, and then also on the case study and some of the follow-ups after I came to EPA. But this is a great site. It's a nice case study on the role of the conceptual site model to aid an expedited site characterization using Triad at the Poudre River site in Fort Collins, Colorado. Quickly, what did the site look like? Well, in the bottom left-hand corner there, you see there was a historic manufactured gas plant. And then along the Poudre River, there was, at the time, if you see the footprint in the middle there in black, there is a community center, and that community center was subsiding into the landfill next to the river, which had not been formally closed. So there was a series of targeted brownfields assessments that were being done to help close the landfill, deal with the subsidence of the community center, and during low flow, of course, their contractor, I think it was February, went down to have some lunch by the beautiful and scenic Poudre River, and of course found this bowling ball size. This is low flow, so just a foot or so of water in what during other times of the year can be a raging river, but easily could see these bowling ball size masses of a DNAPL sitting on the bottom of the river, which when they were poked or disturbed created a sheen, as you see here in this picture. So we had a lot of disagreements about what the conceptual site model for the site looked like. EPA, one of the potentially responsible parties, and some of their consultants had different theories about how the stuff had actually been placed into or had been made it to the river. Our theory was that it was moving in the subsurface from the historic manufactured gas plant and making it to the river. Other consultants have had theories of a dumping scenario and other things of small amounts of contamination from the historic manufactured gas plant being disposed of next to or dumped into the river. And so we were able to use those competing conceptual site models to design an investigation that helped answer those critical questions. And here, basically what they did is in low flow, February time of year, they've rerouted the river. So you can see behind the railroad tracks, that's where the river is. They've got a cofferdam there and a series of large HDPE pipes that lead up and over behind the trees and then go downriver several hundred yards. So they were able to basically divert the river during low flow conditions, pipe it around several hundred yards of the river, and come in and do, in this case, a trenching investigation. And their theory was, oh, we'll find a little bit of contamination and we can dig it out and the project will be done. Of course, they started trenching and napple began to pour into the trenches. Napple that they had previously insisted was not mobile and could not be coming from a manufactured gas plant. Many of those assumptions proved to be incorrect, and so it was determined that there's quite a bit of material moving in the subsurface. So we followed that up with a huge high-resolution site characterization effort using mobile labs, direct push, soil gas, passive diffusion bags, and a variety of other high-resolution techniques to really map out impacts from this and determine where this stuff was moving in the subsurface. And turns out that it was basically moving through moving along fracture in the shallow subsurface, and then entering into some shallow bedrock, and then being hydraulically pulled up back into that section of the river. And so EPA came in. Here they are installing a sheet pile wall that's keyed into the bedrock. They put hydraulic controls around the sides, and then they also restored the river with natural grasses and rocks, and kind of this is what it looked like post excavation, post installation of the sheet pile wall and hydraulic controls to capture that mobile napple. And all that happened very quickly. The installation of that remedy was done by EPA's removal program. The characterization and the installation of the remedy was quite rapid. And ultimately, the city was thrilled because they were able to build the first Gold LEED certified community center in the United States. Gold LEED is a energy efficiency and building efficiency certification, and that is the Northside Astland Center, which now sits over the closed landfill, up gradient from the sheet pile wall and the work that was done in the river, and the community is thrilled to have such a wonderful building. And so one of the things I like to do for gas stations in particular is, over the years, Tom Cady and I have done some work for the Office of Underground Storage Tanks to try to help them, integrate some of these high-resolution characterization tools and strategies. And just to give you some perspective, this is going back several years, but each year the Office of Underground Storage Tanks rolls up all of the regulated underground storage tanks from all of the states. And you could see in 2016, at the end of the fiscal year, there were 560,000 federally regulated underground storage tanks at more than 200,000 sites. They had completed a number of cleanups, but something like almost 71,000 remain in the system, the quote backlog to try to address. And those sites had a lot of those challenges that I talked about early on: limited funding. Many of them are complex sites, as the easy ones were cleaned up and dealt with relatively easy in the early stages of the program. And some of these sites even have remediation systems in place where it can be quite expensive to continue to operate inefficient systems if you are not achieving your remediation goals in a timely fashion. And that was the same experience that we had in Superfund, the same experience that we had through Superfund optimization. In fact, by that point, we had done more than 200 sites and 20 years worth of experiences, and we certainly shared that with the tanks community, and many of the best management practices that came out of Triad and resulted in high-resolution site characterization were from those experiences and shared with the tanks universes. In fact, I even, when I was with the Office of Superfund Remediation back in 2012, we did a series of trainings for some of the states to assist them with integrating Triad elements and high-resolution site characterization tools. And again, we had to overcome some of the perceptions that, El Naples sites are not as complex as Superfund sites. Certainly they can have monetary challenges, but we were finding that, in our experience, that some of those sites can be just as complex and just as challenging to achieve the objectives. So we also looked at tribal sites, tribal leaking underground storage tanks. We've had some great successes there, but we don't always get permission to talk about those. We did a series of pilots looking at some of those tribal sites in 7 different regions, or 7 sites across multiple regions, and we found very similar types of findings that we found in the Superfund program, where we had uncertain or imprecise conceptual site models. We had remedial systems or remediation systems operating with really no defined closure strategy, which makes it very difficult to determine when you're done. Potential receptors not evaluated or not being monitored, insufficient functionality of the remediation systems, all of those things stemming from challenges with some of the characterization. And in fact, I like to use that little triangle up in the corner to sort of illustrate, the fast, cheap, good triangle. You can get it fast and cheap, but it probably won't be good. You can get it good and fast, but it probably won't be cheap. Or you can get it good and cheap, but it probably won't be fast. So, if you're lucky, you get 2 out of the 3. So folks keeping that in mind as they try to use their limited resources to address these challenging sites. So Tom, Katie, and I actually wrote a series of two articles on whether or not to use high-resolution site characterization at tank sites. They're in that LUST line, the leaking underground storage tanks bulletin for the tanks community. All the regulators and folks have access to that. And in 2018 and 2019, we put a series of articles out there looking at whether or not folks could, to see if we could increase the use of high-resolution site characterization tools at state and tribal tank sites, drawing on our experience using those tools and our takeaways from the challenges of remediation through our optimization program. And so this is a nice article that goes through sort of thinking about and trying to turn some of the paradigms around on how we address these sites, going after source areas, thinking about El Naples as source areas rather than always necessarily chasing low part per billion of certain contaminants, which in some cases the states, they have to do that. That's how the regulations are written. But there's still opportunities to integrate some of these tools and strategies in there. In fact, several states provided testimonials in part 2 about the way they use these types of tools like MIP and LIF and some of these tools at state sites. Some key takeaways from the article was the importance of time, determining when the release happened and moving quickly to address the release. The longer you wait, the more likely it is to impact groundwater or become a diffusion issue or get into fractured rock systems, and those become very, very costly. So there is an importance of time to address, to try to go after these sites, but also the cost of being fooled. We have many examples of doing low resolution characterization efforts. I called it the 1 up and 2 down, but a common practice in some of the early days was to place a monitoring well, quote, up gradient, and then 2 monitoring wells, quote, down gradient of a site, and use that to characterize the site. We found that's wholly insufficient in most cases to do. So folks are now, of course, integrating all of these great tools. But we also really identified some strategies to attack and identify root causes, those high mass, low footprint areas. Where is all the mass? That's what's leading to the dissolve phase challenges that you're having in groundwater and other things. Can we identify that with these tools, attack it like we've been trying to do in the Superfund program, and see if we can increase our efficiencies and timeframes to remedy completions. And so part 2 of the article, the series, part 1 was really to look at sort of the tools and strategies that might be available to folks in the petroleum tanks universe. And then part 2, we really wanted to look at the cost versus benefit, which can be pretty challenging to do since, only a small percentage of the sites were probably, all across the United States are actually using these using these tools at most sites. In fact, we had a series of informal discussions with state regulators from Virginia and Alabama, Colorado, and others talking about how they integrated high-resolution site characterization into their programs. A couple of state testimonials in the article as well. But, in talking to not all of the states, but a fair number of states, it was kind of, ballparking it, but coming up with maybe 5 to 10% of the sites are using some form of high-resolution site characterization. They're using MIP, they're using laser-induced fluorescence, or the newer optical imaging profiler, optical image profiler. We were able to back out some ballpark numbers. These are based on 10-year averages, so the Office of Underground Storage Tanks helps roll up some annual numbers from all of the states, and we can look at, average costs, or I did a 10-year average for cleanup and the amount of money that the programs were spending on cleanup and remediation, and it turns out the average across 10 years for all of the sites was something like 45 or 50,000 spent on characterization, and about twice that on remediation. So that's similar to the experience we had in Superfund, in that typically we would spend several orders of magnitude more on remediating a site than we might be able to with characterization. The other question, or the question became in the article, whether or not we should recommend doing high-resolution site characterization at every site knowing nothing versus select sites. And we went through an exercise of looking at, the average cost of characterization, the average remediation, and then the final costs. And I couldn't necessarily make a strong case for doing it at every site, but I think it's fair to say that as sites started to creep up over those averages, or they had specific challenges identified, that the high-resolution site characterization tools would be cost-effective and beneficial to the projects. And even some states had either they had an informal program or a more formal program where they were either request or require a contractor, for example, to do a high-resolution site characterization investigation if they were planning to implement any sort of in situ injection strategies, chemical oxidation, etc. That the states are definitely catching on that integrating a high-resolution site characterization effort into that really for those types of costs is going to have significant benefits on the performance of that more costly remediation effort. So how well do you understand your site conditions? A bit of a pun here, but we use this one a fair amount in the high-resolution site characterization class. The same happens in LNAPL sites, where the technology that you're using will influence your understanding of the contaminant distribution and the conceptual site model. So if you're using monitoring wells versus using direct sensing tools versus using other analytical techniques, all of those influence the development of your conceptual site model and your understanding of what's happening at the site. Now, we've been pushing, the use of scale-appropriate measurements for a long time to help us deal with, changes in hydraulic conductivity and the heterogeneous distribution of NAPLs in the subsurface. In our experience, monitoring wells are wonderful tools for monitoring. That's why they call them monitoring wells. And in some cases, they may not be the optimal investigation tool. But historically, that's how we've investigated sites. We use monitoring wells kind of placed out with what we jokingly call a hope and poke scenario, or a poke and hope scenario, where you go out and you poke a hole and you hope you find what you're looking for at certain depths. But the challenge with those wells, of course, remains is that you could have depth integrated flow weighted averaging happening across large well screens, which can help you miss or not be able to discern those transport zones and mass storage zones that are so critical to address in the subsurface. And then, of course, all of those monitoring wells have life cycle costs. Once you put it in the ground, you have to develop it, maintain it. Typically, it becomes part of the monitoring effort. So I love to use monitoring wells. I just like to be really sure of where I'm placing them, where I'm screening them, so that they're very effective in helping with monitoring in the future. So, and of course, the challenges that go with looking at LNAPL in wells. Been a lot of research in that, but certainly LNAPL inside, looking at the LNAPL thickness in a well, for example, doesn't tell you a whole lot of what that thickness may be in the formation. In fact, when it comes in and fills up that well, it may be coming in from a relatively high flow, high concentration zone that is a fraction of what the well screen is. So you're again, using LNAPL thickness in the well to try to understand what's happening in the formation can be a challenge. But there's actually a series of tests that we recommended or that we've looked at for determining actual thickness using well bail down tests, slug tests, trying to estimate K values based on changes in oil thickness and rising water tables. So there's some better techniques that we've found to help us try to understand just how much NAPL might be in the formation near a well. And lastly, I've asked Tom Cady of the Environmental Response Team. They are the field arm of the Office of Superfund Remediation and Technology Innovation. They implement the Superfund program. And Tom will be presenting a case study on a petroleum site very close to their office in Edison, New Jersey. Tom has more than 30 years of experience with both with EPA and also working with characterization and remediation contractors throughout his career. And he spends a great deal of time recently with distance collaboration tools and bringing together all the stakeholders to help us evolve our conceptual site models in real time and quickly and rapidly make decisions on environmental sites.